In the first module, we introduced the pharmacokinetic parameter of volume of distribution, and we said that this is the parameter that relates the total amount of drug in the body with the concentration of that drug that we measure in the plasma sample. Now, in order to calculate the volume of distribution, we need to know two things. One is how much drug we have in the body, and the second is what the concentration is in the plasma at that time. The problem is that as soon as we give a dose to an animal, or a dose of a drug to an animal, that animal's body starts excreting the drug. So we don't know how much drug is in the body except exactly at that time when we've given the full dose and we know that the amount of drug that is in the body is the dose. And then the other problem is that it is practically impossible to take a plasma sample and give the drug at the same time, so that we have a plasma sample at time 0, which is the time when we're given the drug, and at the time when we know how much drug is in the body. So what do we do about this? Well, this is where pharmacokinetic modeling starts coming in, and what we need to do is that once we have our pharmacokinetic data, our time versus concentration data, we fit a model to those data, and then we use that model to predict what the concentration would have been had we taken a sample at time 0 when we gave the drug. Okay, so I am going to show you how we do this with a very simple data set using Excel. So this is a data set of time concentration data. It is an ideal data set, so there is no noise. It is also a data set that is very simple because it is for a drug that was administered intravenously and a drug of which the pharmacokinetics is best described using a one-compartment model. So if we plot these time concentration data on a linear time versus linear the actual drug concentration, we see that the concentrations decline steadily over time, but it's a curve that the data form a curve. So this is very difficult to fit a model to these data unless you're using a software program that is able to do nonlinear regression and fit models using nonlinear regression, but we're using Excel. So one thing that we can do is that we can linearize or transform the data so that it falls on a straight line, so that it is linearized. So let's do that. So what we do is that we take the natural log of the actual concentrations. That's our first step. And I'm taking the natural log, which means it's the log to the base of the number e. You can also take the log to the base 10 or log to any number really. But convention is that more generally that it's either the natural log or the log to the base 10. And now we can replot these data. So let's make a copy of our plot. Let us reselect the data so that we are selecting the natural log of the concentrations instead of the concentrations themselves. Now let us format the axis so that we can look at these results a little bit better. And here we have it. And let's do one more thing and remove that smoothing line, because what we're going to do is that we are going to add a trend line, and that trend line is a straight line because the data fall on a very nice straight line, and then we can request that the program displays the equation on the chart so that we know what the equation is for the straight line model. And there is the equation. Okay, so now we can use this model. And what we're interested in is what is the y value when x is 0, because when x is 0, that is time 0, which is exactly the time at which we have administered the dose to the animal, and there has been no time for any of the drug to be excreted yet. So we plug x equals 0 into this equation, and that will allow us to calculate y, which is the natural log of the concentration at that time. So let's do that. Times 0 plus 6.2146. And no surprises there, the natural log of the concentration at time 0 is 6.2146. Now, to know actually what this is the natural log of the concentration, so let us calculate what that actual concentration is, and that is e to the power of that number, and that gives us the actual concentration. So the actual concentration at time 0 is predicted to be 499.99, or for all practical purposes 500 micrograms per milliliter. So how do we use that now to calculate what the volume of distribution is for this drug? Well, we know that the volume of distribution is the amount of drug in the body at time 0, which is the dose, divided by that concentration. So the volume of distribution for this drug is 10 milliliters, and that is what we have calculated. And notice that our volume of distribution is 10 milliliters and not 10 milliliters per kilogram, which is what we most often see in the literature when we look at the literature for veterinary species and the veterinary scientific literature. And that is because I gave you the dose in micrograms, not micrograms per kilogram. If I had given the dose in micrograms per kilogram, then we would have calculated a volume of distribution that would have been milliliters per kilogram. Either way is correct. You just need to know what you're doing, so which method you're using, so that you give the correct units so that it can be interpreted correctly. And that's it for now. Thank you.